So I'll present a joint work with Zihan, Ryan, and Yukshi, and with Andreas Veneris and Fan Long from University of Toronto. So I will present our work on SigVM, which enable event-driven execution for smart contracts. So there was already 2 lectures on blockchain, but I will do a quick introduction about blockchain with specificity to Ethereum blockchains. Is everything fine?
I can make it a part of the country back. Yeah, go ahead.
Okay. Okay. So blockchain, we can think of it as a distributed computing platform where we have a chain of states and we have transactions that are kind of a transition between the states, and those transactions are organized in blocks, and those blocks are permanently stored on the platform. So the main concept in Ethereum is what we call smart contracts, which are simply like code that execute the blockchain transaction. And those smart contracts are usually written in the Ethereum bytecode for running on the Ethereum blockchain. Simply, smart contract is constituted of fields to store the state. So here we have the token smart contract, and we have 2 fields to store the token state. The second component of smart contract are methods, which are called by transaction. We can distinguish 2 types: method that will query the state and method that will modify the states. So here we have the transfer method, which does transfer of asset from one address to another. The third component are events, which are used to log the state changes and which are only like write only. So here we have an event transfer. So when the transfer occurs, we will emit an event like to record that there is some transfer that happened. So the main focus of this work is on events. So currently event in EVM, the main idea why we have event is to store some blockchain logs and to allow contract to communicate to off-chain entities important state changes. For instance, like there are crypto wallets that people use to hold their crypto assets. So for this crypto wallet to follow the changes on the chain, they will listen to this event logs to say that there is some transfer happened from person A to person B. However, this event cannot be used by the contract themselves. So contract cannot directly listen to events emitted by other contracts. And this is for current state of blockchain is a limitation, because now contract become more complex, and with the increase of uses of decentralized protocols like some contract might need to interact and to react to the state changes in other contracts. For instance, how people do this now for the existing protocols is to use some off-chain relay server. So this is there will be some relay server, they will listen to the logs on the blockchain, and there will be in other contracts some kind of function that we call POC function, that this server will send some what we call POC transaction, which are regular transactions that will be calling this POC function to react to these events. However, this defeats the purpose of decentralization, because here we have a central point, which is this off-chain relay server. So if they fail, all of this mechanism will fail. And this defeats the purpose of what we are doing is decentralized computing. Let's look at this in a specific case study. We will look at the first case, which is the MakerDAO, which is a decentralized protocol on Ethereum, and it provide collateral-backed stablecoin called DAI, where one DAI will be around $1 US. And how this stablecoin is managed is to use some kind of collateral that will be proportional to the amount of DAI that is held by the owner. So this should satisfy some formula that this ratio should be bigger than some threshold. And in order to compute this ratio, the MakerDAO will rely on the prices of cryptocurrency. For instance, the price of Ethereum against the US dollar, which fluctuate every day. So it needs some oracle of prices to give it this information. And so if like the value of this ratio drop against below the threshold, we need to collateral to liquidate the collaterals. So MakerDAO is implemented as a set of smart contracts that interact. So there is median, OSM, spot, and other smart contract. The median receives the price from some oracles, and then it will use the relay server to propagate the prices update to other smart contracts. On March 2020, there was a price drop and there was a network congestion on the blockchain Ethereum. And there was a delay in the price updates, and the protocol was working with the outdated prices, which resulted in collateral liquidation, which resulted on loss of 8 million. Let's look at another case study, which is Augur. Augur is a decentralized prediction market to bet on future real-world outcome. It implements a process to finalize the betting round result and to start a new round in some smart contract called Universe. And every 24 hours, the sweep interest function in this smart contract has to be executed to do this process. Since it's not possible to do this like a periodic call to this sweep interest every 24 hours, the contract will rely on this relay server to poke this function every 24 hours to do this process. Now I will say our proposed solution to eliminate this reliance on off-chain server. Our proposed system is called SigVM. It natively supports the event-driven execution. It is an extension of the EVM, the Ethereum virtual machine. It allows to execute the signal transaction asynchronously. It has an incentive mechanism for the execution of this transaction, and it also implements a contract locking to protect contracts while like the asynchronous signals are waiting. Then I will present an evaluation of SigVM, where we implemented in a tool called SigChain. Then we took a set of smart contracts that are in some of the most popular protocols, and we implement them to use like the new operation of SigVM. And we evaluated the runtime overhead in the SigChain, and also we evaluated the smart contract gas consumption. And I will finish my talk with a conclusion. So let's start by an overview of the system. So SigVM is designed as an extension of EVM to allow smart contract to listen and respond to event in other contracts. It eliminates the use of off-chain relay server to simulate event-driven execution. So MakerDAO no longer need off-chain relay server to propagate price or update across its contract. And Augur no longer need off-chain server to periodically poke the function every 24 hours. So how SigVM does that? It introduces a new primitive called signal events. A contract can declare a signal and emit an event of this signal. Another contract can bind a handler function to this signal. So one event of this signal is emitted, the handler gets executed as a signal transaction. So let's look at an example here. Assume we have contract A and contract B. Contract A has some event alpha. So here we are working under the Ethereum context. So here, like Ethereum will work by some maintainer of data will first call the contract A, and contract A will emit some events login alpha, and the relay server will be listening to this event and will be poking the contract B. In SigVM, we eliminate this relay server. We no longer need that. When contract A receives the updated data, it has a signal event beta that will emit an event of this signal, and contract B has a handler function that is attached to that signal, and when the signal is emitted, the handler function will get executed automatically. So, as I said, SigVM is designed as an extension of EVM, so we support all operation of EVM, and we add 5 new operations for signal event. First one is create signal, to create some signal. The second one to delete a signal. The third one to bind some function to a signal. And the fourth to detach the function from the signal. And the last to emit an event of that signal. We also extended the Solidity compiler SolC to support high-level programming that use those low-level features. So contract may need some buffer period to react to event from other contract, because maybe like they have like some period where they need to ensure that what they received as a data is correct, or maybe the administrator need like to wait for something in order to ensure that. So like that, we might need like to have some asynchronous communication between the contracts. So that's why, for instance, in MakerDAO, OSM contract introduced 1 hour delay to the price feed in order for the people that manage MakerDAO to authenticate whether the price update are correct or not, or they are false. So here, existingly, how they do that is they have some guard statement to ensure that there is 1 hour delay. So to handle those cases, SigVM is allowed to specify delay period between event emission and the execution of signal transaction. So for instance, if we are like replacing this POC function with SigVM, we'll be like emitting some signal delay price, and we'll say that you need to delay 1 hour. So in this case, automatically you don't need this guard statement. You don't require, because the runtime system itself will ensure that at least it will wait 1 hour before executing the signal transaction. So this allows also to simplify the code itself. So if we look at the Augur system, like the sweep interest in the universe contract must be executed every 24 hours. So here we need like some mechanism to handle this kind of delays, and automatically always like repeat the same process every 24 hours. So here how we implement this concept. When we construct the universe contract, we emit some delay signal that has 0 delay, and we have some update handler function that will going to call the sweep interest, and it will going to emit some signal that will execute a signal transaction in 24 hours. And doing that signal transaction, it will execute this handler in 24 hours and emit another one. And this will continue as a loop. So this is here how it's implemented. So in the constructor, we have the first signal that we emit. Then when we enter the handler for the first time, we emit a signal that has that delay that is calculated based on the block rates to ensure that it is 24 hours. So that means like every time you execute that function, you will emit a signal. So you are kind of in open loop that never stop. So in EVM, a transaction has an associated gas fee, which is kind of how much resources that this transaction need, which is paid by the transaction initiator. However, in SigVM, when a transaction is triggered, all associated handler functions get executed through the signal transactions. So it's undesirable that the entity that is triggering the event pay the gas for all those signal transactions. Since usually like this entity, you can think of it as a service provider, like an Oracle maintainer that triggering an event to update the price. So it doesn't need to pay the prices for the handlers that are executed by other contracts. So for this, in SigVM, a smart contract that binds the handler function to some signal, it's the one that pays the fee of the corresponding signal transaction. So to incentivize miners to prioritize signal transaction over regular transaction, we introduce an incentive mechanism. So another parameter in the bind operand, we call it the gas incentive ratio, where the signal transaction gas price is the average gas price of the block plus multiplied by 1 plus the gas ratio. Also, since like now, like signal transaction pay more gas price over other regular transaction. We fixed some parameterized threshold of like how many signal transaction can be packed in the same block. So like we fixed the threshold like of 1/10 of the total block gas limit. So this can be changed to allow regular transaction with cheap gas price to be packed as well with signal transaction. You can ask this question if like if some contract is listening to this event and some spurious events are emitted, how can these contracts like rescue itself? So here, a contract can stop listening to signals by detaching its handler function from that signal. Also, another issue that we need to resolve is that interfering transaction can interact with contract before it integrates the updates that are coming through this asynchronous signal transaction. So for this, we introduce some lock mechanism to allow a contract to block transaction while it's waiting for some asynchronous transaction to get executed. So this will allow like contract to stop entity that they don't trust from interacting with it until like it updates to the critical state. So here, like the last three parameters of the bind function, it contain parameters that enforce a lock mechanism. So the first one is a Boolean, which when it is true, only specified addresses can call a list of specified methods. So this allows, for instance, if you are an administrator of that contract, you can specify that while your state is while you are in a transient state, only you as an administrator can call the contract maybe to fix some kind of bugs or something like that. Now we're going to present an experimental evaluation of the SigVM system. So we implemented SigVM in a tool chain called SigChain, which is an end-to-end blockchain platform that supports the SigVM. SigChain is an extension of Conflict Trust, which is an EVM-based public blockchain client. We augmented the blockchain state with the signal events, and also we extended the transaction pool to enforce the locking mechanism. We also extended the Solidity compiler to support writing smart contract in high-level programming language. So we have 5 new primitive: signal for signal declaration, handler for handler function like specify, bind some function to signal, and detach to detach that function from the signal, and to emit an event of a given signal. So to evaluate SigVM and SigChain, we collected a benchmark of 23 smart contracts from 13 popular decentralized applications that include MakerDAO and Uyghur and other Compound and Dutch Exchange, and these are mainly popular decentralized protocols. So here we have some data about this smart contract, and also we have the data when we implement them using the SigSolid programming language. So we can see that the implementation effort of this smart contract is small, since we only change 5 primitives that are going to be added, which in total result on 3.5% changes. We also tested the runtime overhead. So we looked at 4 types of transaction. The first, the normal transfer of the native token. The second is contract call, which reads the state. So we use the peak function of MakerDAO median contract. The third is a POC transaction, which is the old way to do signal events, where we use the OSM contracts POC. Then for the signal transaction, we use the one that will replace this function. So, and we executed each type of transaction 1,000 times. And we compared against Ethereum clients. So here are the data of the experiment. We can see that there is no big performance overhead. The biggest overhead was for the contract call when we read the state, which is around 2.7 microsecond. And we can also notice that for the signal transaction, it's a bit faster in the SigChain than the corresponding POC function. And this is because we did some simplification that, for instance, for before, as we saw before, the required statement is no longer needed. So we can do code simplification, which will improve the runtime. We also evaluated the gas consumption. So here, for this, we collected data from the 10 most recent POC transactions for 4 the apps, like MakerDAO, Compound, and Multisig, and historical price feed. And we looked at 5 functions. So here we have we calculated the signal transaction gas fee by taking a gas incentive ratio of 0.1. And we can see that the increase in the gas fee of signal transaction over POC transaction is reasonable. Even we pay more gas price per gas unit consumed. So this is because the most of signal transaction consume less gas resources than their counterpart. Now I will conclude. So SigVM provides a solution to natively enable event-driven execution. It's developed as an extension of EVM to allow easy integration for EVM-based blockchains. And an experimental evaluation shows that SigVM is practical. Thank you.
All right, we have lots of time for questions again. Maybe I can start. How do you guarantee that a handler will always be handled? I mean, if there's lots of, it could be lots of contracts are waiting on the same signal because it's, and then is there some guarantee it will definitely be processed
Yeah, so yeah,
under a certain time limit?
Theoretically, there is no guarantee. And in practice, one thing that you can do is to incentivize miner to pack your signal transaction by giving more incentive. And also you can protect your own contract by using the locks. Because here, since the gas mechanism in public blockchain is based on which one pay more prices. So if you are going to integrate SigVM in public blockchain like Ethereum, you cannot dictate how miners are going to select transaction other than by the simple mechanism of paying more gas.
Right, but even if you use a lock, if you have too many clients are waiting on the same signal, you need a mechanism to see who wins who gets to execute first, right?
Yeah, but here, all of those, you can think of them as independent, those handlers.
Okay.
They are themselves, they don't need to depend on each other. They just will depend on the signal event when it gets emitted. Mm-hmm. They will automatically get executed, but they shouldn't depend on each other, because each one can when it call the bind function, it can specify its own let's say gas ratio, because it's a parameter of the bind function, and also they can specify which kind of locks they want to enforce. So it's depend on which handler function wants to do what.
Okay.
I hope that was clear.
Yeah.
Thank you for the talk.
This is a proof of concept implementation for the EVM. Are there any other blockchains that implement this sort of event-driven functionality already? Because there's a lot of them out there. I don't know the details.
So I think there is what we call there are blockchain there is Celia language that has this message passing concept, which is implemented in Zilliqa. So there are also other blockchain, but EVM based blockchain, which is the majority of public blockchain, they don't support event-driven execution. like they support like ad hoc solutions that are based on this relay server, like which are like kind of some of them like I presented the most simple one, but some of them like include like smart contracts that are deployed that you can through them route some kind of event-driven execution. But here it's an ad hoc solution, and it's like it's usually like can be also error prone and.
Thank you.
If you want to ask a question.
Yeah, maybe a rather simple question. I might not have caught what you said about the possibility of like, how do you make sure that the event you're handling in your handler is actually the one that your intention is to handle? Is it possible to spoof events?
Yeah, so here, like in the event, when you do the binding, you specify the address of the contract you want to bind to. So you already know the contract, and also you specify the name because contract can have multiple signals. You also specify the name of signal. So here, like you already know that there is a signal in contract that is specified by this address. So you already know that information. And maybe in the future, maybe some exploiter can exploit that contract and control it, maybe in some way. And in this way, that's why also detach function will be very useful. If that contract in the future like become like spurious, you can detach your handler from it, so you don't listen anymore.
Okay, so how about the deadlock? I mean, would adding this extension could easily leads to code that are deadlocking?
Yeah, so like there can be created deadlocks. Like like in the paper we presented like a case where there can be some deadlocks where like one contract listen event from other contract, and that one will listen an event from the other one. So here there will be a deadlock. But here to prevent this deadlock, they can like each one can whitelist the other one. So because I presented a like whitelisted of addresses, so one smart contract can say, okay, I will allow that one to execute while I am waiting for my signal transaction. And this will resolve like the deadlocks. So here,
I guess it's not really deadlock, right? Because there's always a finite amount of gas, so it won't deadlock. It will just use up all the gas, which is not what the designer want.
Yeah, it's kind of deadlock in the term of denial of service.
Right.
Like you don't fully terminate the execution, either because of gas or something, but it's kind of the service in this case will not be finished. So yeah, it's not like the deadlock where the state doesn't advance or something like that.
Okay, let's thank you again.
Thank you.